Section 13.1 Vector Functions and Space Curves. So, in Calculus 1, you looked at one function and one variable. In this chapter, we're going to be looking at several functions of one variable. And so, a vector valued function is some function from, let's say, the real numbers, some field, some complete field, to some vector space, and this is called a vector function. If, let's say, V is R, if F here is R, and V is R3, and R is the vector with components F, G, H, then the real values functions F, G, and H are called the component functions of this vector function. And we write the vector R of t as equaling the vector with components F of t, G of t, H of t. Or I can write it as F of t times the standard basis I, G of t times the standard basis vector j, plus H of t times the standard basis vector k. We can analogous to what we did in Calculus 1, we can define the limit of a vector function as just a limit of those component functions. And so the limit as t approaches a of r of t is the vector with components limit as t approaches a f of t, the limit as t approaches a g of t, and the limit as t approaches a of h of t. Provided that the limits exist, of course. Otherwise, well, the limit will not exist. Continuity. The vector function r is continuous at a if the limit as t approaches a of the vector function r at t is equal to the vector valued function r evaluated at a. Space curves. Let f, g, and h be C0 functions, so continuous functions defined on some interval I, then C equaling the set of ordered triples such that for all t in the interval I, x equaling f of t, x is equal to f of t, y is equal to g of t, and z is equal to h of t. So I here is some interval, let's say in the real numbers. A knot is an embedding of a circle, S1, into a three-dimensional space, R3. So in the book, they give you this example. X equals 2 plus cosine 3t over 2 all times sine of t. Y equals 2 plus cosine 3t over 2 all times sine of t. Z equals sine 3t over 2. And so this figure that we've drawn here is the trefoiled knot. And this is how it looks from the perspective that they show you in the book. Okay, so let's do some examples. On page 893, find the limit. And so I have here the limit as t approaches 1 of this vector I'm going to find the limit individually of all of these, but let's write this as, let's factor out a t, then the t minus 1's cancel. Square, I don't have to do anything with this. T plus 8 radical and sine pi t over ln t. Well, let's use L'Hopital's rule. So this is a 0 over 0 form as t approaches 1. And so I can use L'Hopital's rule. The derivative of sine pi t is pi cosine pi t. The derivative of ln t is 1 over t. And so this is the limit as t approaches 1 of 1 rad t plus 8 pi t cosine pi t. And so this is going to equal it's t approaches 1. Oops, why is that? Why did I write 1 there? The t minus 1's cancel, and so you just have a t. As t approaches 1, well, t approaches 1. T plus 8 approaches 9. Square root of 9 is 3. Pi times t is just just pi. Cosine, and then pi times t is, again, pi. Cosine of pi is 0 times pi is 0. And that is your limit. In exercises 7 through 14, sketch the curve with the given vector equation. Indicate with an arrow the direction in which t increases. So I have here cosine of t I minus sine t j plus sine tk. So this is just going to be a circle, and it's at a weird sort of angle, so it's kind of at a semi 45 degree angle here into this plane. And so, well, it's 45 degree to that plane. Exercise 52. The view of the trefoil knot shown in figure 8 is accurate, but it doesn't reveal the whole story. Use the parametric equations. X equaling 2 plus cosine 1.5 t all times cosine t. Y equals 2 plus cosine t all times sine t. Z equals sine 1.5 t. To sketch the curve by hand, it's viewed from above with gaps indicating where the curve passes over itself. Start by showing that projection of the curve onto the xy plane has polar coordinates r equaling 2 plus cosine 1.5 t, theta equaling t. So r varies between 1 and 3. Then show that z has a maximum and minimum values when the projection is halfway between r equaling 1 and r equaling 3. When you finish your sketch, use computer to draw the curve with the viewpoint directly above and compare with your sketch. Then use the computer to draw the curve from several other viewpoints. You get a better impression of the curve if you plot the tube with radius 0.2 around the curve. Use the toPlot command in Maple, or the tube curve, or tube command in Mathematica. Okay, so we actually, in class, I showed you several sketches using Wolfram Alpha. So let's do this. R squared equals x squared plus y squared. Well, x is 2 plus cosine 1.5t and times cosine t. So let's square this. Y is 2 plus cosine 1.5t times sine of t. So again, let's square this also. So let's square this. So this is equal to, well, I could factor out a 2 plus cosine 1.5t. What remains is cosine squared plus sine squared, which is 1. And so, taking the square root of both sides, I have that r is equal to 2 plus cosine 1.5t. Tangent of theta is equal to y over x. And so this is equal to 2 plus cosine 1.5t sine t over 2 plus cosine 1.5t cosine t. The 2 plus 1.5, 2 plus cosine 1.5t's cancel. So you just get sine over cosine, which is tangent. And so this says that theta is equal to t. So long as you are, well, restricted between, let's say, 0 and pi. So I have that cosine of 1.5t is between plus and minus 1. Therefore, if I add 2 to every side of my equation, I have that 2 plus cosine 1.5t is between 1 and 3. And so this says that r is between 1 and 3 by what we did above. And so the extrema for z equaling sine 1.5t occurs when 1.5t is equal to 2n plus 1 over 2 pi. So an odd multiple of pi over 2, which implies that cosine 1.5t is 0 when r is equal to 2. And so I can sketch the graph of this. And so sketching the graph of this parametric representation, I get that we start here, we go up, and then look like this, and then look like this, and we go over, go around, we go over, and then come back here. And that's what the sketch looks like. And so that's it for section 13.1. See if I can try to. There, I got it finally.